Hey everybody, second to last video here on day 3 recursion, talking about binary numbers. So you've probably heard about binary numbers. They're kind of a big deal. Your computer uses binary numbers to represent every single thing it works with. Zeros and ones, binary, base 2, as opposed to the base 10 we conventionally use. Um, in this exercise, we'll be working with binary numbers as Coq represents them, not as they really are represented on your computer as a string of ones and zeros and sort of memory and all of the detailed low-level stuff that we talk about there. You'll learn that in CS 105, computer systems. For now, we're just going to talk about them as a way of representing numbers different from the unaries. So this will be a little bit different from most presentations of the binaries you've seen, but it'll let us talk about it, I think, in a fairly clear way, and later on we'll get to do some proofs about it. Let's take a look. So we're going to use the type bin to talk about binary numbers, the same way we use nat to talk about unary numbers. And they're going to represent the same naturals. They're going to represent numbers from 0 on up. So we have bz here, that's the binary 0. And we have t2 of n here. That's, you can imagine sticking a 0 on the end of a binary number. So that would be n0. And then you have t2p1, that's sticking a 1 on the end of a binary number. This has the effect, if n is a series of binary digits, has the effect of doubling n. The same way that sticking a 0 on the end of a base 10 number has the effect of multiplying that number by 10. Sticking a 1 on the number has the effect of doubling it and then adding 1. So we've given these constructors names that are sort of mnemonics for that. T2 times 2, T2P1 times 2 plus 1. So to write that out, 2 times n, another way of seeing that, format it nicely. Right, so these are the constructors. To really get a sense of how they work, you're gonna want to write some examples down. That's how anyone understands anything in computers. Is examples first. So let's look at some. We'll do side-by-side comparisons where U underscore is how we'll name the unary number and B underscore is how we'll name the binary one. We'll just take a look at them. Next, after that, we'll have you write some conversion function. That's going to be the sort of the main homework here. Okay, so U0, B0, O is the name of the constructor for 0 in the unary naturals, and BZ is the name of 0 for the binary naturals. Great. Okay, so how would we represent 1? Well, in the unary numbers, it's just S of O. We've already seen that. In the binary numbers, we would write T2P1 BZ. Why is that? Well, this is, if BZ is 0, then this is 2 times 0 plus 1, which is equal to 1. Perfect. Now, Coq sort of speaks these unary naturals natively. So if we sort of like print U1, it'll print out 1, but it doesn't speak these binary numbers natively. So it'll print out this sort of gobbledygook of T2P1BZ or whatever when we do it. We're going to write conversion functions to solve that problem. Let's move on. How do you represent the number 2? Well, in unaries, you just stick another S on there. For the binaries, we have to think a little bit. Well, if T2B1, this is the same as U as B1 up here. If you multiply 1 times 2, well, that'll get you to 2. So great. So this is 2 times 0 plus 1, which is equal to 2 times 1 is equal to 2. If we were to write these in in a better notation, we might write U2 as slash slash tick tick, right? It's just 2 marks on the wall. B2 we would write as 1 0. Right? So this part is 1 and this T2 is the 0 we tacked on at the end. I'm going to make a separate video where I go through this relationship where we talk about the digits and the Coq constructors in more detail. And that's going to help you with the last exercise you have to do here. But I'm not going to do any more detail on that right now. Okay, here's 3. For unaries, stick another S on it. For binaries, well, what do we do? Well, if this is 1, 1 times 2 plus 1 is 2 plus 1 is 3. So here's how we represent 3. What about 9? Okay, at this point you start to see like, oh wow, unaries are maybe less cool than you thought. There's a lot of S's. Sort of like tough to count them. You kind of gotta like put your finger on your screen. Try not to smudge it. For the binaries, you start to see that like, oh wow, this is a little more concise. So let's see what we get. This gets us to 1, times 2 gets us to 2, times 2 again gets us to 4. 4 times 2 plus 1, you're looking at 9. 11? Okay, take my word for it that U11 worked. For B11, okay, let's check. So here's 1 times 2 gets us to 2. Times 2 plus 1 gets us to 5. Times 2 plus 1 again gets us to 11. Perfect. Okay, so in the text, we talk a little bit about what's going on here, show how to get the binary numbers. Um, what work do you have to do? Okay, first, we want you to write a function, inker, that takes a binary number and gives you a binary number 1 higher. Then we want you to write a function, bin to nat, that takes a binary number and converts it to a unary natural number that has the same value. So B11 should map to U11, B9 should map to U9, and so on. Next, we'd also like you to write some tests. Right? This is just a we give them names or whatever. I'm sorry. You should just write 5 compute tests here. So write 5 of these that say, oh, here's what I expect it to do. And so put those 5 computes in here, and those will be part of the manual grade. That's the first part of the exercise. The second part of the exercise, you should only attempt when you've finished the first part. It's 4 stars. This is going to be easily the most challenging thing we've done yet. You're really going to have to think about it. Okay. Write a function nat to bin that converts natural numbers to binary numbers. Okay. Now, you might think at this point that if we start with a binary number, convert it to a natural, and then convert back, you'll get the same one we started with. But it's not true. It won't happen. We want you to write, just in a comment, what's the problem? What goes wrong? Why don't you land on exactly the binary number you started with, necessarily? And then lastly, we want you to define a function normalize that says, okay, I'm going to take a binary number to one that will have that property, right? That can do this round trip. Right? So if I start with a binary number B, I convert it to a natural, and then I convert it back to binary, I'm going to get normalized B back out. Okay. This is a hard problem. You're going to have to think really carefully to even figure out what it is you need to fix. If you get stuck, you can write this or something similar, right? You'll need to fill in type, right? You have to write what that would be. You can write something like this for nat to bin and normalize, and the autograder will still be able to work. If you're stuck, we'll talk about it. We'll have 2 days to work it out. I have confidence that most of you can, at a minimum, get the idea, and many, if not all of you, will be able to define this function just fine. But it's okay if you can't. Okay, cool. The exercise after that is we want you to do some part of this for trinary also. So define a type using inductive that's like binary, but represents trinary numbers. That is to say 0, 1, and 2, base 3. And then write a function to convert a trinary number to a unary nat. You can name it anything you want. We'll figure it out. If you want to, go ahead and write nat to trin, and then what your normalized function would be, because your data type will have the same normalization problem. You'll need some helper functions to get it all to go. Okay. I'm going to talk about this last paragraph in a separate bonus video. That's it for now. I'll do 2 more after this bonus video about the what's happening here, which I think I'm going to dedicate a separate video to, and then the whiteboard going over the binary numbers. All right, see you soon.